At this point, we're ready to add on a couple of statements that are equivalent to ones that we already had. So here's another theorem, an extension of the one that we had earlier. It says if A is an n by n matrix, then the following are equivalent. A is invertible. Ax equals 0 has only the trivial solution. The reduced row echelon form of A is the identity matrix. A is expressible as a product of elementary matrices. Those ones we already had. So now I'm going to put on two more that are equivalent. It says that Ax equals B is consistent for every n by 1 matrix B, and that Ax equals B has exactly one solution for every n by 1 matrix B. Okay. So I've already proved the first four are equivalent to each other, so I'm not going to do that here. I'm just going to look at A, E, and F. And what I'm going to do is I'm going to show that, let's get a little bit bigger here. I'm going to show that A implies F implies E implies A. So that all of those are equivalent, but since A was equivalent to the others, then these are all equivalent. So the thing is, for A implies F, this was actually in an earlier video. We proved that if A is invertible, then this system right here has exactly one solution. In fact, the solution was A inverse times B, right? Just multiply both sides by A inverse. So that one we already did. F implies E. This one's obvious, although I'm a little nervous every time I say that because I know that professors have a habit of saying things are obvious when it's obvious to them, but not obvious to the student. But let's look what F says, that this system has exactly one solution for every matrix, every n by 1 matrix B. This says that this system is consistent for every n by 1 matrix B. Well, to be consistent means you have to have one or more solutions. Well, if you already know that you have exactly one solution, well, then you have one or more. So certainly if F is true, then E has to be true as well. The work now comes in trying to show that E is equivalent to A. So here we go. I'm going to assume that this system is consistent for every n by 1 matrix B you choose to pick there. Okay. Now consider these systems. I'm choosing particular values of B. I'm taking 1, 0, 0, 0, 0, 0. I'm taking 0, 1, 0, 0, 0, and 0, 0, 1. That is, I have n different systems here with a 1 in the first spot, or the second spot, or the third spot, or the nth spot. Right? One for every spot in that n by 1 matrix B. So because I know that this is consistent for every B, each one of these systems is consistent. So there's a solution for this one, which I'm going to call x1. There's a solution for that one, which I'm going to call x2. And these are matrix x1. So x1 is a whole n by 1 matrix that's got numbers in it, which are the solution to this system. Right? So I've got n different matrices, n by 1 matrices, which are the solutions to this these n systems. Now I'm going to make a matrix by taking these n column matrices and putting them all into one matrix. So the first column was the solution to this system, the second column is the solution of that system, and so on down to the last column being the solution to that last system. Okay. Now look at what happens when you multiply A times this matrix B. Well, how do you multiply matrices? Well, I'm going to take the first column of this matrix here, and I'm going to multiply it by the rows of A, which give me the first column of the product. Then I'm going to take the second column, multiply it by the rows of A, and that's going to give me the second column, and so on down the line. So the columns look like just A times the first column, A times the second column, and so on. Okay. But notice that A times the first column, well, this was a solution to, come on now, slide down. This was a solution to this system. So AX1 is going to be 1, 0, 0, 0, 0. AX2 is going to be 0, 1, 0, 0, 0, 0, and so on. So what we have here is that this matrix is the identity matrix, the n by n identity matrix. So what happened? We just had A times B equals I, so B is A inverse. And we have that A is invertible because we just found the inverse. So E does imply A, and hence A, E, and F are all equivalent. Okay?